Okay, next talk is the ADaPS from Seoul National University. The presenter will be the Jaume. So we are actually behind, so you can start.
Good afternoon, everyone. My name is Jaume Mateu, and together with Professor Bernhard, I will present this paper, ADaPS, Adaptive Data Partitioning to Parallelize CNN Inference Resource on Constrained Hardware. And these days, as we know, the AI is more popular than other models, so we try to move CNNs to edge devices for privacy, and the main problem of this is that these devices usually have low memory and low processors, so what we try to solve is dividing this so the inference is not underperformed and we can still keep the privacy on those devices. We try to focus on heterogeneous devices since usually we try to use anything that we have in our labs, and we try to do the partitions in an efficient way so it doesn't take forever to compile. Here is a simple example of what we try to do for the motivation. Usually we have different devices, and those devices have different speeds and different characteristics, so we try to divide it, and this can generate some data transfer between them when we try to communicate between them, and we try to find the best partition between all of the devices. Some of the challenges that we found during this research was the complex network graph path and which order do we have to process, or how should we cut the path to process in a better way. In our case, we use a greedy path approach. The other problem that we find is the exponential search space. As we know, as the number of devices increases and the size of the layers also increases, those search spaces become exponential. So it's really difficult to represent and to fit all the all the space in a memory. To do that, we created a procedural partition tree structure. And the other problems we found out is how do we search this search space, and because usually it takes a lot of time. So the optimizations that we applied is alpha beta pruning together with some dynamic programming. When talking about these networks, we also have to take into account that they have different operators, so each node is characteristic by some operators, normalization, convolutions, and another type of operators. So we try to use the main characteristic of these and generalize them so we can find groups that we can divide easily. And finally is how do these devices communicate? Usually the two solutions that there are centralized or decentralized. We opted for decentralized because as the number of devices increases, the overhead is a big problem. So our main contribution is a flexible technique for different types of hardware, together with an efficient search space that it takes a reasonable time to search with a good solution, and finally an end-to-end layer search that will take into consideration all the layers of the network. Since we talk about our decentralized system, we wanted to compare with the other projects that they had decentralized options. This was BBGraph and EdgeFlow. The key differences between those related works is that BBGraph uses a greedy approach where it divides all the layers into the same sizes, and it keeps all the layers separated so it doesn't take into account the information of previous layer or the next layer. For EdgeFlow, the key difference is that it uses linear programming to search the vast search space, and also it takes into consideration direct layers, but it doesn't keep forward to the next and next layers. In our case, we use a recursive approach where we start searching the first layer, then we include these results into the next layer and keep going up and down through the network until we find a consistent solution that is good. To do that, we require some hardware specifications like the processing speed, the bandwidth, and the network information, for example, the size of the output, the size of the inputs, the weight sizes, the dilatation, stride, etc. Here is a simple example of our algorithm. We can divide our algorithm into 3 steps. One will be selection, search, and backpropagation of the results. In the first example, we have the selection until we get to the terminal node, which will be the layer 0. When we get to the terminal node, we do a search space between layer 1 and 0, and then we backpropagate, as we can see in the number 2, to the previous layers, the partial results. In the first one, we can see that the red arrows will denote that there are word results, so they don't have to be stored when we do the backpropagation. And when we do the next selection, we do again the selection, search, and we compare both of the previous results to see which one is better on the fourth one. If the result is not better, we just can skip the next search and go to the previous layer and keep doing that up and down until we reach the last layer of the path. As I mentioned before, the challenge of how to represent these enormous possibilities is we did a procedural search space that will construct the partition on demand. This tree search is divided in 3 levels. The first level will be the layers, second level will be devices, and the third level will be the start and the end of the partition. If we look closely at in the red selected partitions, the example is presented on the right bottom. Here we can see a direction size output that we can see that it starts at 0 and 3. This is the first partition for the first device, then it goes to 2 and 6 for the second device, and 6 and 9 for the third device. This tree is not all kept in memory, but it uses also it uses copies of themselves, as we can see on the top layer 0. When we select one distribution, it will ask for the stored tree, and it will be the same on all of them. For the optimizations, first we will start with dynamic programming. As we were doing the search, we saw that this tree will keep repeating itself multiple times, as we can see in different colors. In here we see the red colors will be one subtree, green color another one, and the blue one, it will be another one. This keeps repeating recursively the more devices that we have. One key thing to notice is that these subtrees, it will always start when the third level is a start point. And the next, using the previous optimization of the dynamic programming, we use the pruning method that it will avoid already partial results that we know from previous subtrees. So we can skip many of the results and not do all the calculations. And this is how we achieve the vast improvement on time. So for the evaluation, we use Raspberry Pi 5 and 4. We created a simulator using the PyTorch and their distributed library. For the network, we choose old and new ones, more simple, more complex, and smaller and bigger. As we can see, biggest one is BGG, smallest one will be MobileNet, B2, and the more complex ones and newest as the Inception, B3, and Hardcore NAS. For the experiments, we run the compilation in maximum of 5 times. This was the case for BGG16 usually. And to validate it, we run 100 times each configuration independently. We tried 2 and 4 nodes approaches. In the 2 nodes, we can see that the data transfer is really improved. All of the results are normalized to Edgeflow. And then we can see an improvement in the inference time average of 15, being the best ones in the simplest networks and a little bit worse in the more complex due to the greedy path search. For 4 nodes, we see the same trend, around 15, 18% of improvement. However, the data transfer is a little bit worse due to the number of synchronization between all the devices. So now for the pruning, as I mentioned before, the pruning is one of the most important parts to keep the time reasonable. Here we can see in base log 10 that as we increase the number of devices and the freedom of the partitions, these numbers become immensely big. Finally, some conclusions. We found that we presented an efficient algorithm to keep search space in a reasonable time with a good solution. And some of the ongoing work that we are trying to do is LLMs with the transformers and RNNs with the recursive path. And finally, one final thing that we would like to improve that other papers also doesn't do is how to find a better past search. Thank you for your attention. Any questions?
Okay, thank you for the great talk. And any questions?
Thank you for your intriguing talk. Does your work cover transform operations or reduce operations?
Transformers, it doesn't. With another future work.
Then I'm curious. I'm curious what portion of the overall latency is attributed to that kind of operations.
Like which one?
Reshape or transform or reduce operation.
We don't have an actual analysis of operator by operator. Usually these operations, because they are all connected to one device, usually we don't consider that, but we try to consider it later. One of the other future work is using division of fully connected networks using weight division.
Are they crucial for gaining performance?
Huh?
Are they crucial?
What do you mean? What are future?
The operations including reshape or reshape, transform, or reduce operations.
Usually, I don't fully understand what you mean as if they are crucial, but we don't usually reshape them. We usually allocate them in memory. If you mean that, I don't fully grasp what you mean.
I mean that we have lots of operations regarding transforming shape.
Yeah.
And it seems like that your work does not cover this kind of operations, right?
But this is depending on the network, isn't it?
Yes.
Yeah.
So I would like to know what portion of the overall latency is attributed to this kind of operations, because if they are not crucial, then we don't have to take care of it, right?
Yeah, usually those reshape and everything, it's just treated as any other operator. So we don't have an analysis of operator by operator. So I cannot fully answer these questions of how is good in performance or not.
Thanks.
Okay, any other questions? Okay. Oh, yeah.
Okay, I have a very quick question. You've compared your work to previous approach, but how much reduced your latency compared to just running on a one device solely?
We don't have this here, but usually the problem is sometimes they don't fit into one device, so we cannot compare it even against those.
But maybe a mobile net is very small to run on a single device, like a Raspberry Pi.
Yeah, we don't have the results here.
Okay, thank you.
Okay, so we are out of time. So thank you for the talk again, and we will move to the next talk.